Okay, so here we have an air bubble at the bottom of a lake. I probably didn't need to do it there, but whatever. And it's 40 meters deep. So then the pressure on the air bubble, or at the air bubble, is rho, so the density of water, sorry, start over a little bit here. So the pressure is going to be 1 atmosphere plus the force over the area. So the area here is, and so we've got the force due to all this water is going to be mg, where m is our volume of water times our rho, so our density of water. So this is V times rho times G over our area. But of course, volume is area times height. So our pressure is 1 atmosphere plus rho G H. So for rho, I'm going to use just 1, and so the pressure for the bubble 40 meters below the surface is 1 atmosphere plus 1 times 9.8 meters per second squared times our height, which is 40 meters. And that's 1 kilogram one gram per liter, or 1 gram per decimeter. Oh, sorry. I'm not going to use 1. Now I see what I wrote there. 997 kilograms per meter cubed is what I'm going to use. There we go. Okay, so now my units are a little bit funny here. So this is going to give me 1 atmosphere plus 390,824 pascals. An atmosphere is 101.325 kilopascals. So my pressure is 101.325 kilopascals plus 390.824 kilopascals, which is 492.149 kilopascals. There we go. Okay, so we've got a bubble at the bottom of a 40-meter lake. The temperature is 4 degrees. Celsius. And now for the second part, the bubble rises to the surface, and where the pressure is this 101.325 kilopascals, our temperature is now 22 degrees Celsius. And so it asks what is our volume in this case. We are given in the question that our volume initially is 19 centimeters cubed. Okay. So using, we can use ideal gas law here. So for our initial case, we've got PV equals nRT. We've got pressure, volume, and temperature. So we can solve for nR. We know what R is, it's a constant, but we might as well just leave it in there because it's not going to change. So our pressure is 492.149 kilopascals times 19 centimeters cubed times 1 times 10 to the minus 2 meters per centimeter cubed over our temperature, which is 277.15 Kelvin. So our temperature is 4 degrees, which is 277.15 Kelvin, and our temperature here is going to be 290. So plus 273, so 295.15 Kelvin. So our nR in this case comes out to be 0.0337392, and this is actually in pascals meters cubed per Kelvin. So I did also multiply by 10 to the minus 3, or 10 to the plus 3 here. Okay, so then at the surface, we have PV equals nRT. Again, we want to know the volume, so our volume is nRT over our pressure. We can use our nR that we just solved for, so 0.0337392 pascals meters cubed per Kelvin. Our temperature is 295.15 Kelvin, and our pressure is 101.325 times 10 to the 3 pascals. So we can see that our pascals cancel, our kelvins cancel, and we're left with a meters cubed answer. So 9.828 times 10 to the minus 5 meters cubed, which we can put into centimeters cubed by multiplying by the relevant factor. So our meters cubed will cancel, and this will be 98.28 centimeters cubed. So the volume they solved was 101. I presume that's just differences in, so their temperature was they added 273, not 273.15, so that's going to change some things. They also used 10 to the 5 pascals equals an atmosphere, which is not quite right. They just used 5 atmospheres, so a lot of rounding differences there, but I think for the most part it's correct. All right, and I'm actually going to sign off there and say thank you all for watching. I hope you enjoyed this. If you do, please subscribe to OneClass. If you want to leave questions, please follow the links below the video. This has been Jeff Krause for OneClass.